Yes, good evening. So today we will discuss sixth assignment. There will be 25 question on solar photovoltaic course. So let's discuss the first question. First question: the silicon solar cell has a band gap of 1.52 eV electron volt. Find the maximum wavelength for this perovskite solar cell. So this is the question: how we can find the maximum wavelength? Are you listening me? My voice is clear.
Yes, sir.
Okay, thank you for your response. So let's discuss this question. Option will be four option is there. So how can you find maximum wavelength? What is the concept behind this? Do you know? Let's by lambda over u. Let me write simple first, then convert h nu over nu equal to, so we have to use this relation for maximum wavelength. We can come h by e. But let me tell you what is the concept. Let's say we have a material band gap. This is valence band, upper side is conduction band, and band gap of this material is delta E equal to 1.52 eV. Okay, we know that if incident light, let's say photon, has an energy equal to h nu equal to, this is band gap of material, let's say should be greater than or equal to for material to absorb this light or photon. Let's say p photon, incident photon. Yes or no? Only material can absorb the light equal to or greater than the band gap to the material. Then material can absorb. Am I right? So let's put this formula here. If let's say this is lower, then this will be high. So we need a minimum energy. Minimum energy should be band gap. So this is up to maximum. At max, they will be equal to the photon energy. So incident photon has energy equal to the band gap. For this has a maximum lambda. For this, clear? Let's say we have two lambdas. Let's see, lambda 1, lambda 2, given E2. Let's say this is maximum. This is also the maximum, but lambda 1 corresponding to the, let's say, band gap max, and lambda 2 max has lowered the energy of the band gap, let's say that much. If lambda is maximum, then energy goes down. You know, here this is an interesting. This session, so we have discussed some fundamental questions, and up to your knowledge, I can't say what is your knowledge, what is your topic knowledge. If you want to watch or discuss something, you must. We will enjoy the session. Okay, thank you. So clear to you this question. This is a good concept. If not, please let me ask. How we can find the maximum wavelength? Clear to you? Let me tell you another way. First, let me explain the maximum minimum concept. Let's say we have same material, same band gap, but this is lambda 1, this is lambda 2. Let's say lambda 3. Okay, let me put in order, otherwise you will confuse. We have same material band gap, but different lambdas. This is lambda 1, this is lambda 2. Lambda 1 is less than lambda 2, less than lambda 3. Okay, These are lambda, and lambda 2 equal to the band gap, Ag of material band gap. Let's say this is band gap, and lambda 1 is less than to the band gap. We have to put in another. Up to you, clear now? We know equal to Hc by lambda. If lambda is minimum, then energy is maximum. This is min, this is max, inversely proportional to. This is clear?
Yes, sir.
Okay. Let me put in energy respective. Lambda will be confusing to you. Incident photon has energy E1, E2, and E3. And E2 incident of photon energy equal to the band gap of material. If material can absorb only the energy, photon energy has greater than or equal to of the band gap. Only material absorb the light. Okay, only this condition. So we have let C by lambda max. At maximum wavelength, this will be goes down if this is goes up lambda. So we have to find maximum at wavelength. This will be equal to the, this is, let's say, photon energy equal to the band gap. This is the concept here. Okay, clear?
Yes, sir. Yes,
So
sir.
okay. So if minimum can exceed, because energy lambda is minimum, energy is maximum. So minimum case is not the limitation, but maximum is the limitation. So this is concept, and you can easily find, 1240 divided by lambda in nanometer. This will be in electron volt ev. So we have 1.52 ev, 12.4, and lambda max. We equate band gap equal to the incident photon. Then we will find the maximum wavelength. So please calculate this equation. Lambda max equal to 1240, 1.5 in electron. This is will be in nanometer. Please calculate this. So, delivered
815.794
at, yeah, you are
more.
right. So answer B is correct. Greater than or equal to. So we nearest is this at 15. Beyond this, material cannot absorb the light. Lambda minimum is not problem, but maximum is problem. So let's discuss next question. The approximate thickness in micron of the absorber layer in monocrystalline silicon solar cell is thickness monocrystalline silicon solar cell in micron. How can we decide the material should be that much thicker that can absorb the maximum light, total light? Let's say this is the thickness of the material T. So for this equal to an exponential alpha T. But if light is goes to inside, let's say I naught is the initial intensity, goes to intensity deeper than goes to into the deeper inside the material, intensity goes down because material get absorbed and there is a coefficient of alpha, absorption coefficient. So silicon around 300 micrometers in micron will be the thickness in micron. That should be the length absorb layer that can give the optimum output. Okay, we will discuss the question in upcoming slide next later. But please remember this thickness, approximate thickness of the thin film or monocrystalline silicon solar cell will be 300 nanometer. Oh, sorry, in micrometer. Let's discuss next question. Extract power from a solar cell can be maximized by. How can you maximize the power extraction from the solar cell? These are four options: minimize center resistance, series resistance, maximize, or minimize. So let me discuss first. We have ideal this. This is J. This point is JSC VOC. So this side gives series resistance. This is side is shunt. How can you calculate the series shunt? And let me we have ideal practical solar cell ideal this type, which has series also has a shunt. This is real and this is ideal. So equal to my R V by R equal to 2 resistance. Yes. So if you have I IV curve, let's say this. So how can you calculate the slope? Inverse slope di by dv. This is slope at point do you want. So inverse of the slope give the resistance. So this is, let me convert in this way. Inverse of this. So inverse of this dv by di dv by di. Take the inverse. You will get the slope. So inverse of the slope you will get the resistance. Okay. So slope this side parallel to the x-axis, slope will be tan theta equal to, you know, so theta will be 0 here, so slope tan theta equal to 0, slope will be 0. So inverse of 0 is infinite. Take the inverse, you will get the resistance. You will get this side is 0 because perpendicular to the x-axis will give theta equal to 90, tan 90 is will infinite, and take the inverse of this, you will get the slope. So this will be 0. So what is the question? You want to maximum power. So for maximum power, ideal case series resistance should be 0 and shunt resistance should be infinite. So maximum shunt resistance and minimum series resistance. Maximum how much? Should be infinite. Minimum should be tends to, then you can get maximum power. In picture, let me give to you two picture, then you can compare. Let's say we have two solar cell curve, IV curve, one this, there, this type. So which one is more efficient, first or second? You have to compare always to the ideal. Let's say we have ideal black. So you can also calculate the area under the curve. 5 JV curve. This is V, this is J. Maximum area, maximum power. So black has most, then blue, then red. In this way. Okay. So question if like that, what please, let's say this is 3. Which one has more power? IV curve. Please arrange in order. So first is 3, then is first, then is this is 3, this is blue is second, then red one. Okay, let me point out clearly. Yes, this is red is 1, then blue is 2, and black is 3. Ideal. So 1, 2, 3. We have 3. 3 is maximum. This will be the power extreme maximum order. Clear? So you have to always check. You have to compare always the ideal one. Okay, any doubt? We have IV curve of the solar cell. This side is series, this side is shunt. Inverse of the slope of the curve gives to you resistance. Slope inverse equal to the resistance. Please remember this. This is simple form equal to IR. So in ideal case you can also check CN series resistance. This is the circuit for solar cell. For ideal you can see series resistance should be 0, shunt resistance should be infinite. And this black one has maximum, then medium, then small. Shunt resistance goes like that. So and series here you can check goes to higher. This is lower, then higher, then higher, then higher. Okay, so you can also compare. Clear? Please respond. Clear or not?
Yes, sir.
Okay, so you have to just nothing. This is if this like that curve, then series resistance equal to 0, and this line parallel to the x-axis is Rs equal to infinite. This is the ideal case. If deviate from this side series goes, and this goes like that center resistance go to lower. Idea is rectangular like so. Let's move to the next question. Solar cell has band gap. We have two band gap. Sg1 and Sg2 are illuminated by one sun irradiation. Then which of the following is expected to be true considered for only optical losses? So let me give it to band gap is proportional to direct the viewership directly. Now we can check our answer according to this band gap is higher, then VOC is higher, then first option is correct. But what about the current density? Let's say we have two material Sg1, Sg2. Sg1 is higher, okay, greater than to the Eg2. So VOC is directly proportional to, but what about the current density? This is correct or COD? According to you, please let me know. What is your answer?
Sir, J mean?
Current density. So current per area. Current density. J means current density. So current density is reverse. Let me sorry. This is the relation between VOC and current density. If VOC goes up, current density will goes down like that. Theoretically, this is calculated with respect to 1.1 sun illumination. What is one sun irradiation? Do you know? Do you have any idea?
No, sir.
Okay, let 1 minute. If we have a spectrum like that from the solar cell, oh sorry, our sun, this is visible lens, and yeah,
Yes, sir.
ultraviolet.
I see first lecture.
Hmm.
Solar irradiance.
So this is so when we measure the solar cell efficiency, we have a standard. We have to illuminate our solar cell one sun radiation, equivalent power to the spectrum from the from the sun. So my pencil is discharged. Give me 1 minute. According to you, in visible range, you will get maximum intensity from the sun. Yes. After this,
Yes, sir.
you have a less intensity. So from this one sun radiation, according to the band gap, you know the relation band gap. How can absorb the material light according to the band gap? That much. Maximum wavelength. You know, we have already calculated in first question. So at max wavelength, you will get the power. Beyond this, you didn't get. So band gap also play the role here, and radiation intensity. So we have theoretically limited. You can see band gap or VOC is increases, current densities decreases. Why zero point 0.5? Let's say zero point 0.5 has a band gap. Why is maximum current? Let's say we have a 1.2 electron volt band gap material. Why is current is less? Can you correlate here? Can you find the lambdas? 4.5 eV electron volt and 1.2 eV electron volt. Please find the first wavelength. This is wavelength 1240 divided by 1.2 nanometer. But for this, Okay, this is maximum. So 1.2b band gap material absorb only maximum wavelength for this, and for this is up to this. So for this 1.2 band gap has lower window of the spectrum. Let me give you note number. We have like a spectrum, and we have two solar cell. First is here, second is here, according to the band gap. Which one is EG1 and which one is EG2? This is maximum lambda. Let's say this material absorb this spectrum, whole spectrum, and maximum wavelength up to. And second one, let's say absorb that much only. So which one has more? First and second. If number of photon is higher, then electron hole pair will be higher. Incident photon, let's say, has a 50, then 50 electron hole pair. Its a photon has 100, you let's say get 100 electron hole pair. So current will be higher according to the electron hole pair. J2, J1. So if our concept is that if our solar cell absorb more spectrum from the sun, get number of get number of more photons absorbed, then electron hole pair will be higher. So this is the concept. Okay, let's move for next question. Shunt resistance in the solar cell can be increased by, so these are options and let's discuss the answer. Reduce defect density in the device, reduce non-radiative, shunt resistance, this is non-dependent, but defect density and non-radiative recombination. dark saturation and increase the band gap. Dark saturation current, let's say this we have only we will get the does not affect the this portion. Whole spectrum shift down or shift up. Similarly band gap. So this portion shunt resistance is directly dependent to the material quality. Should be non-radiative. Recombination in the material, so defects free. This leads to less defective. Okay, next. Which of the following is correct ideal curve for the solar photovoltaic? I think we have already discussed in inverse of the JV curve. This J, this is V, and this is VOC, and this is JSC. Let JXC for ideal, derivative of J by P inverse at JSC, or we can say V equal to 0. Should be slope should be this side infinite, and slope this side is should be 0. Okay, so equal to 0, resistance be infinite, and inverse of slope should be 0. VOC at VOC. Okay, D is correct, and V equal to 0 should be infinite. P and D the right option. Clear? Let's move for next question. Which of the following statement is are correct for polycrystalline silicon in comparison to single crystalline? So option very low light absorption, smaller carrier diffusion length, higher defect density, better compositional control, lower defect density. Polycrystalline silicon as compared to single crystalline. So single crystalline is better for solar cell. Why? Has a smaller carrier diffusion length. In polycrystalline has lower diffusion length and higher defect density. But in single crystal has higher diffusion length and lower defect density. That's why we use single crystalline silicon give more efficiency as compared to polycrystalline silicon. And for optoelectronic single crystal silicon is cost is too high. Purity is 99.999. Used in chip design and other purposes for highly efficient defect free. Next question: in a top illuminated solar cell, light coupling can be enhanced by making bottom layer thick, making top layer thin, using anti-reflection coating texture from the front side. So anti-reflection coating is the solution, and second is texturing from the front side. Then can we have enhanced the light coupling? This is proportional to. Next question: which of the following is are favorable for efficient silicon solar cell? Heavily doped base, heavily doped emitter, heavily doped base, and heavily doped emitter. These are same. Okay, this is a typo error. Large diffusion length of minority charge carrier, higher optical depth for radiation energy, below band gap of material, large built-in field. So large diffusion length of minority charge carrier and should be large built and large diffusion length. This is not higher optical depth for radiation energy below the band gap. No. Next question. Which of the following strategies are adopted to improve the current collection from the top of the silicon solar cell? So use of silicon dioxide layer on silicon, deeply breed contact, use of anti-reflection coating, heavily doped near contacts. So for this, deeply buried contact and heavily doped near contact. Okay, this is the strategy for improve the current collection or number of charge carrier. Let's say we have contact. So here is heavily doped. Let's say p beta plus plus is doping here near the contact and buried like contact will use the correct sequence for the generation of the electricity in solar cell. Please answer this question. You have 2 minutes. So correct section sequence is first is absorption, then correct creating of exciton, then dissociation of exciton, then diffusion of charge carrier to the electrode and collection of charge carrier. Okay, this is the process. If the light is incident, then biomaterial is absorbed. First is upon absorption, then creation of exciton, they get energy, then get excited, then dissociation to the respective electrode, then collect by them electrode. Let's see, we have external circuit, we will get here power. Then collection of charge carrier. Okay, this is the sequence. The method to reduce the surface recombination in silicon solar cell are surface passivation and heavily doped rear surface operation. We have two surface. Let's say incident light is H nu. This is front. This side is rear. So heavily doped rear side minus or plus can be and surface passivation. The effects are passivated so that light get entered to the material, not reflected. Okay, next question. Which of the following is are correct for multicrystalline silicon solar cell? So answer is large number of grain boundary in multicrystalline silicon has maximum or large number of boundaries compared to the single crystalline, and large sizes grain size is less or smaller than the device thickness. We have multiple grain boundaries like that. But single crystal like that is, so this is grain and these are grain boundaries. Next, in a silicon solar cell, top contact is buried deeply due to reduce series resistance and increase charge carrier collection. So very deeply strategy is used to first is charge collection, also this series resistance is less. So solar silicon, if the solar cell has less resistance series, is give more power. So that's why this is the strategy is used to improve the efficiency. Polycrystalline silicon solar cell has lower efficiency due to these are options. Sorry, this is A, B, C, and D. So higher recombination and presence of grain boundary we have already seen. Due to the grain boundary, non-radiative recombination and higher get multiple recombination and has many grain boundary. So that's why efficiency is less. Which of the following statement is true? Average answer is B. Carrier diffusion length decreases with increases doping concentration. And other, the open circuit voltage decreases when the lifetime of the magnetic charge carrier is increases. Hmm. The open circuit voltage is increased when the intrinsic density of charge carrier is increases. No. Open circuit voltage does not depend on the doping. Yes. This is dependent to the band gap or Fermi level. Next question. The passivation of the dangling bond in the amorphous silicon solar cell is done by texturing, gathering, SiO2 passivation, and hydrogen passivation. So, hydrogen passivation is used for dangling bond passivation. Next question. For the same level of doping in the silicon solar cell, which of the following is valid? So these are the options. P-type doping, best performs better than the N-type. Best and minority charge carrier mobility is higher than N-type. Minority charge carrier diffusion length is large in P-type. Carrier collection is better in P-type. So carrier collection is better. So P-type dope best perform better than the N-type. And minority charge carrier diffusion length is higher in P-type. Diffusion length is higher, charge collection is higher, and that's why this is give best performance, better performance than N-type. Next question. Silicon nitride NiX coating on the emitter in the polycrystalline silicon solar cell is done for reduce the grain, reduce the charge carrier recombination absorption and absorb the light and give rise to electron hole pair, reduce the reflection losses, reduce the surface recombination, and reduce the defect density in the absorber layer. So answer is reduce the reflection losses. If front side is coating anti-reflection not, so this is reduce the reflection losses. Reflection is incident, reflection and transmitted. So this is we have 120 reflection reduce via NiX silicon nitride coating. Emitter in a polycrystalline. Next question. This is a solar cell device has short circuit current 10 ampere. under one air mass coefficient is 1.5 elimination, which is equivalent to 1 cell. The reverse saturation current is 10 to the power minus 11 ampere. The open circuit voltage at 300 Kelvin. Neglect, neglecting any internal resistance in the cell would be. So we have to find the open circuit voltage VOC. This is the question. These are the four options. You can take 45 minutes for this question. Let me write down V equal to you can use this formula. Please calculate the VOC. You can take 5 minutes for this question. Okay. Okay. So let's put the value KT by Q at room temperature at 300 Kelvin 0.026 volt ln 10 to the power 10 ampere and minus 11 plus 1, which is equivalent to 10 to the power 10 and which is equivalent to the 10 to the power 10 ln 10 VOC After calculating this, 0.5986. So A is the option. Okay. Next question. A typical absorber layer of the silicon, crystalline silicon solar cell absorber has 50% the light with the wavelength 1100 nanometer incident from the M, which is one sun. Assuming that the absorption coefficient infrared is alpha is 10 to the 10 centimeter per centimeter, thickness of the absorber layer. Use this expression. Please calculate. You have 50%. Okay. Please use this information. These are given parameter. You have to find thickness. Let me put down this value. So T per centimeter cube per centimeter. This will be in centimeter. If you put ln2, which is 0.6314. If you want in micrometer, this will be in 6 in micrometer. This will be done. Okay. Next, the silicon solar cell has a band gap 1.12 eV. Find the maximum efficiency of the silicon. So if the incident photon wavelength is 1300 nanometer. So these are the options 0, 11, 18, 25. How can you find? First check this wavelength is sufficient to excite the exciton. So 1.12 eV, lambda max 1240. This is the maximum wavelength. Beyond this wavelength, material doesn't absorb the incident photon. So this is 1300 is greater than lambda max. So this material does not absorb the light and efficiency will be 0. Okay, next question. For high efficiency single junction silicon solar cell, which of the should be done? Emitter should be n-type and very thin as compared to base, and emitter should be p-type. No, base should be thick and n-type compared to emitter, and thick as compared to quantities. Base would be thick and n-type as compared to no p-type. Which of the what affect the EQ external quantum efficiency of the solar cell? Band wavelength of the radiation, absorption coefficient, material collection of charge carrier, incident power density of the radiation. So answer is yes. Band wavelength, absorption coefficient, charge collection. No, this is external quantum efficiency is calculated with respect to the incident power density. Only affected by how number of charge carrier is collected with respect to the incident. So band wavelength of the radiation, absorption how much is absorption coefficient, and how can efficiently collect the charge carrier. Okay, so this is last question for today's session. Which of the technique is associated role are correct among following when improve the device efficiency? So these are the options. Please answer this question. You can take 2 minutes. Use of texturing, increase light trapping, use of buried contact, increase center resistance, surface speciation, lower surface recomposition, use of anti-reflecting coating, decrease reflection losses. So which of the technique associated to get more efficiency? We we have used anti-reflecting coating and surface passivation. Okay. Use of buried contact, increase and resistance. Sorry, this is not correct. Okay, let's use of texturing. So these are the technique. So this is all about for today's session. If you have any question, any doubt, you can ask. Hmm. If no, then let me close the session. Thanks for your kind attention. Okay, so thanks. We will meet again next Monday.